Welcome to the HiRSE-Seminar series on research software engineering in Helmholtz and beyond.
Thank you, Claire, for the nice introduction, and also welcome from my side. And also thank you very much for having me here today. I will start with sharing my slides, and hopefully this will work. So you should now be able to see my slides.
Yeah, that's good.
Okay. As Claire already said, my name is Linxweiler. I'm from TU Braunschweig, and I wear many different hats there. And one of them is also that I'm the spokesperson of the SURESOFT project. And with me in my group, there's also Sören Peters and Sven Markus working on the SURESOFT project. They're not here with me today, but actually they are doing the actual work there. But together with us, there is in total 18 people working on SURESOFT from 7 different institutions and facilities. And they are mostly from TU Braunschweig, but also from Friedrich-Alexander University in Erlangen-Nuremberg. And they are working in different fields: mechanical engineering, civil engineering, chemistry, computer science, acoustics. But what they all have in common is that they all are developing research software, their own research software. And we are in the 3rd year now of our SURESOFT project. And actually the project is coming to an end at the end of this month, at least the first project phase. And what I'm going to talk about today is about the learnings that we and also my personal learnings from this project gained during the 3 years. And the question that I'm mainly focusing on, or the aspects, are why I think that we need more engineering and research software engineering in general, and how to convince people to do that. And the second aspect is beyond tools that researchers already happily adopted from the software engineering discipline, like version control, continuous integration. What else do we need to increase the quality of our research softwares? And I like to start my talks with this gentleman here, with Alan Turing, because I consider him to be one of the first, if not the first, research software scientist who wrote software in order to do his research. And you could clearly see that Alan Turing was a smart guy, because already early on in the history of scientific computing, he made an interesting observation. And I quote in a lecture to the London Mathematical Society, he said that one of our difficulties will be the maintenance of an appropriate discipline, so that we do not lose track of what we're doing. And I think, from my perspective, he's kept right. What I mean by that, we have kind of a credibility crisis. Most scientists agree that at least we have a reproducibility crisis. That means that we cannot reproduce published research results from our computations, neither we nor others. Or we have to retract papers because it turns out that the results that we published, that they were wrong because our computations were wrong. Or we have to abandon code and start from scratch because the person who developed the code is not available anymore, and there's no one understanding the code or being able to run it or even extend the code. And the reason for all that is obviously the quality of our software, and this has to do with discipline. As Alan Turing said, we need to maintain an appropriate discipline. And I think that we as a research community, we should agree upon a set of disciplines like other traditional engineering disciplines do: civil engineering, mechanical engineering. They have rules, they have standards that make sure that their results, their products, are of a certain degree of quality. And the reason why is that our software actually matters. Here's some numbers from Simon Hattrick from the Software Sustainability Institute, and these numbers are from 2017. And already then, 2/3 of all publications indicated a relation to software. And if you look closer, then you can see that 90% of academics use software in order to do their research. and even 70% say that the research wouldn't be possible without using software. And then there's the 56% who develop their own software. And the driving force, obviously, behind all this, why research software is becoming so dominant in the research field is, of course, that digitization doesn't stop at science either. And the driving force behind this, obviously, is Moore's law. And I'm pretty sure most of you are familiar with Moore's law, which says that roughly every 18 to 24 months, the performance of new computer hardware doubles. But I think it's worth looking a little bit closer here because never before in human civilization there has been a technology which gained this exponential increase of 6 orders of magnitude of more performance for the same price after 30 years. 6 orders of magnitude more power. That means also that not only the performance is increasing of our hardware, but also our expectations that we have from our software, from our computations running on these hardware. And this comes with a lot of more complexity, which means that the bar, at least for our PhD students who do the actual work, is rising higher and higher and higher because they have to deal with all this growing complexity. Nowadays, you cannot solve your problem alone anymore. You have to integrate solutions from different people, look at different phenomena at a time, not only fluid flow, but also acoustics and, in our case, fluid structure interaction, and all this adds additional complexity, and that is why the bar is rising higher and higher. The problem now is that 30 years ago, your life would probably have been much easier, and that's the reason why we have to care about how to write our software nowadays much more than 30 years ago. Because, as I said, Moore's law is pretty much unique. And that means also that, and no offense, really, you are all smart people in the software engineering world, but those developments in the software environment space and development space, they couldn't stand this vast increase of performance. In fact, the paradigms that we still use, we know those since the 1960s, namely object-oriented programming, which is really dominant, and functional programming or structured programming from Dijkstra. Those concepts, they have been known in the 1960s, and these concepts are still the same. We are still using those concepts. And to summarize this, one could say, in accordance to Moore's law, that software systems grow faster in size and complexity than methods to handle complexity are invented. So in my view, the only or the best chance we have, and maybe this is changing with AI, but so far the best chance we have is to make the best possible use of the techniques and methods available to cope with this growing complexity. The good news is that if you read Frederick P. Brooks's book about the mythical man-month, then you know that there is evidence that people knowing these concepts, in particular the object-oriented programming paradigm really well, then those people are 10 times more productive than the average programmers. And I'm not saying the bad programmers, but the average programmers. And this is then what people in the Silicon Valley call the 10x programmers. The reality is that we have a productivity crisis. Scientists writing code, they spend 50% of their time finding bugs. And an approach from my side now to explain why is what I've taken here from Martin Fowler is what he calls the design stamina hypothesis. And what we see here is the cumulated functionality over time. And then there is a blue graph and a red graph. And ideally, we would want our software development approach to follow the red graph, which is if you care about your design and if you write high quality code, then ideally you would be able to add more functionality over time in a linear fashion. What we find, and what Martin Feiler finds in industry, is mostly the blue graph. And I think industry and science are very similar in a sense, and I explain why. But what you see is that there is a fast increase of functionality in the beginning, and then the curve slows down over time and targets towards an asymptotic limit. And the reason for this is that in industry, people are striving to get the product out really early on to make money. And in science, it's very similar. We want to get our work done, our software up and running, to produce results that we then can publish in papers to get reputation. And so what we do is we trade quality over speed. We do so quote unquote quick and dirty development. It's not that important that we achieve high quality, but we want to get results early. And so we do trade-offs, and we trade this quality over time. But when you trade quality over time, what builds up is what Ward Cunningham calls technical debt. And the name is well chosen because over time you have to pay back. A debt has to be paid back, and you have to pay interest. And the currency in that you pay back is time. Because whenever you do this compromise, and I'm sure you say, oh, it's very similar to what we do. We say, okay, we come back later and clean it up, but first get this done and get the results and then ship the paper and then we clean up later. But in reality, you will never come back and clean up. And what builds up is more and more of this technical debt. And this technical debt slows you down over time, more and more. The more debt is built up, the more it slows you down. Up until a point where whenever you touch your code, you break it. And you spend a lot of time finding bugs and get it working again. So you have this fear of touching it. And once you have reached this point, it's time to think about version 2.0. And then you start from scratch and all your experience is lost and you have to build from scratch everything you have already done. And then you're also in a hurry and have to get things done quickly, and most likely you end up in the same way. So the only chance you have is to focus on good design, good code, clean code, and sustainability from the early on. That's my idea. Not my idea, no, my view on this. The idea is probably from many different people too. But the idea that we had in SURESOFT is to first step back one step and look at it. What does sustainability or clean code or well-written code, what does it take? What does it mean for us? And we define software sustainability in a way that we said, okay, I started with reproducibility in the beginning. Of course, sustainable software, sustainable research software should support reproducibility. Sustainable software should also be able to endure over time, should be useful over time. That means you should be able to run the code, but the code should also be able to evolve over time. We already saw that there's a time component involved in software, and one of these aspects is that the software should be able to also evolve over time. That means that you should be able to add new features so that the software keeps to be useful for you. With your changing research questions, the software should be able to adapt. And I said we took a step back, and if we look from a very broad perspective, I already talked about complexity. And if you think about what software development is all about, Dijkstra said it's the art of programming is the art of organizing complexity. So we have to deal with this vast increase of complexity due to Moore's law. And Brooks divides this complexity into two parts. One is the essential part, which comes from your research question, from your domain-specific problem. And by no means you can reduce this complexity. You have to address this complexity somehow, either you or someone else. But in addition to this essential complexity, there's also an accidental complexity that adds to this essential part. And this comes from the need of knowing a programming language, the need of knowing an IDE, knowing the terminal, knowing the build process, knowing how to run the compiler. All this adds additional complexity that you need to master. The good thing is that this complexity can be reduced, mostly by the means of automation. You take the human out of the loop, and the human is often the bottleneck, as we will see, in a sense that humans make mistakes. And these repeated things that you have to do, those are very error prone, so it's a good way to bring in automation here. So in SURESOFT, we have this twofold approach to dealing in different ways with the different complexities. On the right-hand side, there is all these tools that you most often probably already know: version control, automated testing in combination with continuous integration, virtualization, Docker, installation and deployment. This is all the things that you can master with tools, that you can master with automation. And this addresses mostly the accidental complexity. But this is not what I'm going to focus on here today. I like to focus on the essential complexity. And this essential complexity requires that we make use of concepts and methods from the software engineering fields that helps us managing this complexity. And of course, the research software engineering community is really heterogeneous, and this is not needed for everyone. Maybe you're in a lucky position that you are a person that for your research question, there is already an application that hides all the complexity from you, that you can maybe automate a bit with a scripting language so that you can adjust it according to your research question. Then probably there is not much need for all these techniques. But maybe that's not you. Maybe there is no such application. But maybe then there is a lot of libraries that you can use. Python is becoming so popular from my perspective because there's this vast amount of libraries that you can use. And then there have been people who already solve parts of the complexity for you. And you can then wire up these libraries together, pipe the information, your data through this, and then you're good to go. But maybe there is no such libraries. Anyways, there is then techniques and approaches from the software engineering discipline like object-oriented programming, already mentioned this, or design principles and design patterns that help you rising the level of abstraction and hiding the details so that the human brain is much more capable of dealing with the complexity. In the research software engineering world, many people are already experts in programming languages. There is lots of people also in my context who know C++ really, really well. They are experts in implementing elegant algorithms in the most efficient way. But combining all these details to a larger application needs additional competencies, needs more than just knowing a language. I compare this, or I like to compare this to writing a novel. Putting all these parts together, having different actors, different roles, a thief, a murderer, a love story, putting all this into a very well-defined context, building an architecture out of the details that then lasts for a long time and maybe involves cliffhangers so that you can add additional stories and additional volumes. It takes more than just knowing the language to be a successful author. And so it takes more to be a successful research software engineer, in a sense, more than just knowing a language. On the other hand side, the language is not important for being a successful novel author. Lord of the Rings works in any language. Spanish, French, English. The language is not important there. It's these other concepts. And the same is true in software. Any language is fine if we focus on object-oriented programming language. It's different concepts that you can apply to any language. Now you might ask, what is then important to be in a to write a successful novel, or what makes a successful novel as compared to what makes a successful software? Jeffrey Carver asked people what they value the most from their software, and most say, of course, functional correctness is very important for them in terms of quality characteristics for research software. Others say it's performance. Some others say it's portability or maintainability. Maybe you would like to add on this. Maybe you have something different in your mind. And while you think about this, I'm going to tell you what I think is most important. And I'm going to take the perspective from Jack Reeves, who has written a paper that is called What is Design? And in this paper, he compares the costs for design of a product to the cost for actually building the product. And I'm going to put my civil engineering hat on for a second. And in civil engineering, we used to spend a reasonable amount of time on designing our products, our houses, our bridges before actually building it. And of course, the reason for that is that it's worth spending this time on designing, because once the product is built, it's very cost intensive to change it. So there is actually no chance, or not a lot of chance, of changing a house or changing a bridge once it's built. And in software, in the early days, we had the very same situation. Hardware was really expensive as compared to the cost for people. So it's worth spending a lot of time on punching your cards and thinking about your program before actually running on this very costly hardware, because the computing time was really, really expensive. But again, due to Moore's law, times have changed and it's shifted. Now the people are really expensive as opposed to the hardware. The hardware is nearly for free, at least when you build your software, when you run the compiler, it costs you nothing. But designing the software, writing the source code actually is really, really cost intensive. And this shift is the reason why we moved from what we call the waterfall, Winston Royce called the waterfall approach, from that we know from the traditional engineering disciplines, doing a large, big upfront design and thinking about every single detail before actually building the software or the product. No, what we find nowadays is that we have this agile world where we have this iterative approach, where we do a little bit of design and then we build it and we look at it and we find out what's good and what works and what doesn't work so good. And those things that don't work that well, then we change those. And then we do another iteration. We design a bit and build it and look at it and look at what works, what doesn't work, and we change again. So again, over time, we have this time component involved here, and over time, we change our software according to our needs. And not only to our needs, but also according to the changing environment. When I started, we used to do our computations on CPUs. Nowadays, we use GPUs to do this, and our software should be able to also adapt to these changing environments. And these environments change over time. So again, there is this time component and the need for change, for being able to change. So we should build our software that it supports change and that change is embraced. So if you think about this, it's already in the name. The name is called, or it's called software. And software implies this flexibility as opposed to hardware. So one aspect in software that we need to address is change. Compared to the civil engineering world, again, this is how a house would probably look like if it would be changing according to the changing requirements all the time. And actually, this is what most of our software also looks like. So now you might ask, so what does support, or what should we do to support change? In the software world, it's very hard to prove being right, but it's much easier. Dijkstra failed with proving software being right. really will correct me if I'm wrong here. Maybe in some sense you can prove being right, but mostly you're not able to prove being right in software. But what's much easier is to prove being wrong. So we should ask the question, what makes software hard to change? And again, we come back to the dominant programming paradigm, object-oriented programming. And Alan Kay, who's the inventor of object-oriented programming, he said later on that he would have been better off not calling it object-oriented programming, but message-oriented programming. And that's because it's all about sending messages between objects. And what we have here is a very simple UML diagram, or rudimentary UML diagram, with three classes. There's a person, there's a car, and there's an engine involved. And what we do is we send the person a message that it's supposed to move. And what the person most often does is the person jumps into a car and tells the car to accelerate. And then what the car does is the car tells the engine to start rotating. So in order to be able to send the person the message move, we need to know that the person understands the move message. And so the person needs to know that the car understands the accelerate message. And the car also needs to know something about the engine, that the engine should understand the message rotate. And from this knowledge comes expectations. We expect the person to understand the message, and the person expects the car to understand the accelerate message. And the same is true for the car and the engine. And this expectation is what builds up dependencies. We depend on the person to understand the move method, and the person depends on the car understanding this accelerate method. And the same is true for the car and the engine. And now imagine the engine would be changed. We would change the engine in terms of the public API. The rotate message is not the rotate message anymore, but the rotate message plus a parameter of RPM, how many rotations per minute. And once the engine changed, then also the car needs to change, because otherwise it wouldn't be able to talk to the engine anymore. So we also change the car. And when we change the car, we also need to change the person accordingly, most likely. And once the person changed, we also need to adapt. We are sending the move message. So what we call this is high coupling. Those classes are very high coupling, are high coupled. And this needs or makes us changing all the classes at once. Once the single class engine changed, we need to change all the other classes. Now you might ask, what's the problem with change? Again, it's the human in the loop. Humans make mistakes, and the more changes you have to do, the higher the risk that you make a mistake and that you break your software. So high coupling is actually something that you want to avoid. Bringing this into context, what I just said is this would be my take-home message for you. Of course, it's all about design or managing complexity on the highest level, but one level below this, we could be a little bit specific and say, how do we do this? We need to design for change by managing dependencies. And we have only limited time here, but there is a lot of learnings that we can make use of from the software engineering discipline. And what I told you here, this is knowledge that has been there since the 1960s, 70s, since the 80s. This is nothing new, but those who cannot remember the past are condemned to repeat it. So we should make use of all these tools available, or methods available from the software engineering discipline, like, for example, the solid principles, design patterns, so that we can build software that is easy to change and evolve over time. And because of the limited time here, I'm just giving a glimpse of what design patterns, for example, are good for. Consider this situation where you have two carpenters talking to each other, and one is saying, how do we think should we build the drawers? On the upper right corner, there's this drawer, they want to build this drawer. And the other one says, okay, Well, I think we should make the joint by cutting straight down the wood and then cut back up 45 degrees and then going straight back down and then back up, blah, blah, blah. No one understands what this person is talking about. So it's on a very low level of abstraction. But instead, it would be much nicer if the conversation could look like this. How do you think we should build the drawers? Well, maybe you should use a dovetail joint or a miter joint. And this rises the level of abstraction in the sense that if both have a common understanding of what a dovetail joint and a miter joint is, they can their communication would be much more efficient than the other was. And that's what design patterns bring into play. One aspect of design pattern. You have examples of well or proven solutions, and plus you have this standardization in communication that is good for documentation, for reading the source code. If you use this common terminology, that's only one aspect of how the usage of design patterns can benefit the quality of the software. And what we did in SURESOFT is that we had this infrastructure of for doing continuous integration and version control on the one hand, and on the other hand side, we created a workshop series that we do frequently, 2 times a year at least, and the next will be in July. So if you are interested in looking more inside of what the software engineering world has available for us, then you are invited to join one of our workshops. The next will be in July, and this will be in presence in Kassel, I think. And also, I'm coming to the end of my talk now. We have a lot of material online. We are reachable on Matrix and have these mailing lists. If you are interested in these workshops, we post the dates on the mailing list. Please sign up there if you are interested in that and want to look deeper into this. And I'd like to say thank you for listening, and also thank you for the German Research Foundation for funding us. And with this, I'm open for questions.
Thank you for watching our seminar. Please check out the slides on Zenodo linked below, and see you next time.